Okay, so we were previously looking at harmonic motion, simple harmonic motion, which meant that it would always continue to be like a sine graph or a cosine graph, sinusoidal. And now we're going to look at damped harmonic motion. So I've said here, we've seen so far that the extension or compression of the spring leads to a force and hence an acceleration, which is proportional to the displacement for some central point. I.e., the more you stretch the spring, the greater the force, and hence the greater the acceleration. And really, it would be the greater deceleration, which is why we had that minus omega squared there. With this force alone, we saw that this resulted in the displacement that follows a sine curve as time increases. But this isn't particularly realistic, okay? There's going to be lots of things that will be more specific than simple harmonic motion. We also know from practice, from real life, that the amplitude gradually decreases over time until perhaps the spring no longer oscillates. So there must be some other force at work. I'm just going to pause here for a second. That last question that Hamza was just talking about a pendulum swinging, if you think about a pendulum swinging, what happens with it after time, after a long period of time? It's eventually slows down, the amplitude decreases, and it will eventually stop. Any ideas of how you think that relationship is between like the amplitude, what's happening to the peaks of the amplitude over time? It decreases. Any idea of how it's decreasing?
Drag squared.
Do you think it's decreasing linearly, or do you think it's decreasing in a... It won't decrease the amplitudes. I'm just talking about the peaks. It's not a constant decrease either, actually. The decrease is actually an exponential decrease. Okay? It's... To begin with, the amplitude like decreases by quite a lot, and then towards the end, it's just like not actually decreasing that much. So the amplitudes will decrease with that kind of exponential decrease, depending on some of the scenarios. But generally, that's what happens when you see it going. So I've said here, this is known as the damping force. The other force at work that is slowing the thing down is called the damping force, and it's proportional to the velocity, which kind of makes sense. The faster it's moving, the more force there is that's trying to slow it down. And K is going to be positive, and I'll show why K is positive. In contrast, the force that we previously saw, which was caused by the elasticity of the spring, was known as the restoring force, because the spring is always trying to pull it back to where it was in its equilibrium, hence it being a restoring force. It's trying to restore it back to normal. Such motion is known as damped harmonic motion. So you don't actually need to memorize this, but we just need to work out what is going on here. For a particle that is moving with damped harmonic motion, we say that its acceleration is proportional to the distance, the velocity that it has, and it's negative because it's restoring it. That force is trying to stop it moving like that. So if it was something like air resistance, we would say that the air resistance on that pendulum that was swinging would be higher if the velocity of the swing was also faster. And there's a negative there because we're saying that K is a positive value, trying to say that it would be decreasing the acceleration. And then we've still got the minus omega squared x as previous. And then what you'll notice that we do here is we rearrange it to make it look like a standard second order differential equation, where we can then set up an auxiliary equation and go ahead with that kind of thing that we have, okay? So the type of motion that you see will depend on the roots of the auxiliary equation. Yes?
So, are you saying the tires also have not simple, is harmonic motion?
So in this particular scenario that we're looking at here, the thing that we're talking about that will be moving with simple harmonic motion is like the whole body of the car. So these are, what do you call these? Suspension. So the suspension of the car is that if the suspension, when you drive over a bump, the car will like bounce up and down, but that would be a really poorly designed car. If you go over a bump and then for the rest of the journey, you're doing a sinusoidal curve. So there's a restoring force, which is meaning that over time, the bumps will like flatten back to normal. And that restoring force is this thing that we've got here, and it's proportional to how fast the car is bouncing up and down. So that's an example of where this gets used in like engineering as well. So the roots of this auxiliary equation will come up with these three particular types of things that can happen. And I'm just going to show you what these look like, and then I'll also show you them on Desmos as well. So the auxiliary equation is clearly m squared plus km plus omega squared, and the solution to this second order differential equation depends on the number of roots and hence the discriminant of this auxiliary equation. So the discriminant of the auxiliary equation is b squared minus 4 times 1 times omega squared, hence it being k squared minus 4 omega squared. If that is greater than 0 with the discriminant, we know that there will be 2 roots. The 2 roots that we would have would be alpha and beta, so the general solution would be this kind of thing that we've got here. And this corresponds to something which is called heavy damping, where there is no oscillations at all. If there are equal roots, we know that we come up with something that looks like this, where we have the repeated root of the alpha, and we have a plus bt. Do you remember we have to kind of add in the same one again for that kind of repeated root? This gives us something which is called critical damping, which is the limit for which there are no oscillations. Do you see with heavy damping, it's looking like it's about to start oscillating. It goes up and then it comes back down again. This one just immediately tends towards that equilibrium position. You then have no roots, which corresponds to light damping, and this is where you have something that is going to be real and imaginary parts. There's going to be complex kind of roots that we've got here. So this e to the minus alpha t, or e to the minus at, what's that bit coming from in the root?
The real part.
The real part, and then the sign of bt is coming from the imaginary part that we've got there, okay? There's no cos because of the same thing that we've done previously of combining the sine and cos together into one single thing, like the harmonic identities that we've seen previously. Okay, so it's just the same idea. If you've got a sine and cos being added and they're both with the same argument, you can combine them together into one single thing just to have a look at this. So this one has light damping because although it is slowing down over time, it is still bouncing back and forth in these in-between parts that we've got. So you do need to know these differences. Critical damping is the one that just goes whoosh straight down to where it needs to be. Heavy damping often has a bump that goes up. It might not do. I'll show it to you on the graph, though, of what that looks like. Light damping is probably the one that makes most sense to real life when you think about trying to, like suspension in a car. It's probably going to bounce a little bit either side rather than just go straight like this. Yeah?
Will we get like a 1 marker saying draw the oscillation?
Probably the 1 marker will say describe the motion, and it might say describe the type of damping. So you would say it is damp. You'd say it's damped harmonic motion. The damping is critical. The damping is heavy, or the damping is light. It's really easy to spot just if you know what this table is. But I'll show you what they look like as a graph here. So let me just open up this graph that we've got. This is no longer simple harmonic motion. Simple harmonic motion means it's the sine curve forever and ever. Damped harmonic motion means that it's gonna stop. Okay, so we're only looking at these 3 different values that we've got here. The red one, what's the red one going to be?
Heavy damp.
It's heavy damping. Good. The green one is critical, and the blue one is the light damping. Let's just get it so that they're slightly thicker. Okay.
Thanks, bro.
Now, it's a bit easier to see them when they're all on one graph. Why the green one is critical? What do you think I mean by it being critical?
There's no
start of oscillation.
There's no start of oscillation, and also, look, it's the green one hugs closer to the equilibrium position far quicker than the other one, than the red one or the blue one. So the green one is the one that will go as quick as possible to that equilibrium position, hence it being that very specific point where the discriminant was equal to 0. So there are different things that we can change here. A is the size of one of the constants here. So you can just see it kind of like increases like how these things appear to be moving. It doesn't do an awful lot that different. This is if I were to change the real part of the root that I've got, which is here. If I change the real part of the root, it seems to be changing like how peaky it goes, really. The B value is these other constants. I'm just kind of wanting to show you how they sort of behave. So after a while, it may look like this red one is critical damping, but it's actually got the start of a little bit of a concave part here. Okay, it's got that start of a little hill, which means it's not going to be critical. And again, no matter what I do for this value of B, oh, actually, that's not true.
Then
It then changes it.
It'll probably still have that curve on the top, maybe.
Let's have a look.
I think it changes the
Oh, no, it doesn't.
Maybe what I've said about critical isn't quite true, but critical is still this one that seems to kind of like head down towards it in that way. I'm not sure. Interesting.
Critical worse than heavy.
Yeah.
Oh yeah, critical is worse than heavy. I'm just getting confused by looking at the colours. So the red one is always... Yeah, but
No,
then...
the red one was critical.
Oh, because now B is a negative value, so it might be something to do with B being a negative value. But look, here we go. You can see why the green one is actually worse. This is what I was looking for. Look, when the green one we're saying is heavy, it's so heavy that it goes to the equilibrium position and it misses it. It goes past it. It goes too far, and so it then oscillates from the negative side to the equilibrium position. But the red one is... Sorry, not the red one. I'm getting all my colours confused.
Yeah, the green one goes under, the red one stays above.
Yeah. Yeah, and the green one is the heavy.
No, green one's
critical.
Don't confuse it. Green is critical.
Oh, then I wonder if that makes sense.
Pink. I think the green one still goes under if you go further to the...
Yeah, it would do. The gist of it is, these are the three graphs. All you need to know is if this is repeated roots.
I was saying the heavy one can become critical.
This is repeated roots. This is real roots.
Yeah,
And this is complex roots.
that's what I think.
I think it's because I was playing around with the coefficients of them being negatives and things. Anyway, going the wrong direction here. There's not an awful lot of stuff that we need to be able to do with that theory. It's more just being able to, can we solve the maths problems with it and have a sense of what those dampings mean. Yeah.
If they give us a graph, it'll be obvious on which one it will be.
Yeah. Yeah, it will be obvious. And if they give you like this here, you can just work out how many roots it's got, and we'll then know whether it's critical, heavy, or light just by doing it like that, even if we don't have a graph. Okay, so we'll have a look at this one, and now we're going to start applying these kinds of things into some examples. So we have got here a particle P of mass 0.5 kilograms moves in a horizontal straight line. At time t seconds, the displacement of P from a fixed point O on the line is x meters. So here's the particle, it's been displaced x meters, and the velocity of P is v meters per second. A force of magnitude x, 8x newtons, acts on P in the direction PO. So this is the particle P. So the 8x newtons is acting to the left. The particle is also subject to a resistance of magnitude 4v. Now, it must be going in the opposite direction to the distance that it's moved, because it says it has a resistance of magnitude 4v. Hence, this leftward force is 8x plus 4v. It's the combination of this force here, and it's a combination of this force here. Then we just have the same old, which is find the general solution, use this information here to get the particular solution, and then do something with it. So there's actually nothing that's really new here, okay? Yeah?
Would the restoring force be just AX or AX plus 4B?
The overall restoring force is 8x plus 4v, but this 8x, if it was on the other side, is kind of going to want to restore it back to the middle as well. They're both wanting to restore it back to the middle. So that's why it's going to damp. It's starting over here. It may still move, and then it may move back like this, and it may eventually settle on O, or it may just go like this and stop at O, which would be critical damping, or it may move like this and then come back to O, which would be heavy damping. So we're going to just figure out which of those three things it is that's actually going to go. So the first thing it wants us to do is to show that this is the second order differential equation. What do you think I can do with this diagram here to show that this is the second order differential equation? What can I do that would connect that diagram about how it's moving and all of that information to try and come up with this statement here? Think of mechanics, because this is...
Acceleration is the second derivative.
Yeah? Don't look at this too much. If I just gave you this diagram, what would you do if this is a mechanics lesson?
Differentiate that 8x plus 4.
No, yeah? Draw the forces. Okay, I've already got the forces drawn. I've already got the 8x plus 4v coming to the left. What do you do with forces if you're interested? Yeah, F equals ma. So we're going to resolve the forces. We think the acceleration is to the right, and we're going to do F equals ma. So my forces, my resultant force is what?
8x plus 4. No.
If I'm resolving it to the right is my positive direction. minus 8x minus 4v equals the mass, which is 0.5, times the acceleration. Okay? There's a lot of blank looks for some very basic F equals ma here. I'm right, this is very strange. It's just F equals ma, okay? Now we can just substitute in all the things that we know. So we just get minus 8x minus 4, v is what? dx dt equals 0.5 second derivative of x with respect to time. Double everything, rearrange it, and you get that. So you get 0 equals this plus this plus this. So it's just F equals ma to kind of establish that thing that we've got there. Now, for part B, we're actually going to do the long part of the question. So let's go supersonic speed through this. First thing you want me to do? Auxiliary equation. M squared plus 8m plus 16 equals 0. So you get m plus 4 squared equals 0. So m equals minus 4. So it's a repeated root. Which type of damping?
Critical.
Critical, okay? It's the critical damping, which means it's going to go from here and it's just going to very quickly go back to the equilibrium point. And I'll graph it afterwards and show us what happens, okay? So we get m is equal to minus 4. So our general solution, because notice it's equal to 0, so it's not any of the ones that need any particular integrals or anything like that. Our general solution is that x equals to
a plus b t e to the minus 4.
Good. That's our general solution. We're now going to try and find out what the particular solution is, because we know this. When t equals 0, x equals 1.5, and the speed is 4. So I'll sub in 1.5 and t equals 0, which is just 1.5 equals a.
Just A because
Sorry.
What do I do to find out how to use this bit? Okay, so I'll differentiate it. dx dt is equal to, let's differentiate this.
minus 4 times by.
Okay, so let's do that then. Minus 4 times a plus bt e to the minus 40
Then times by B.
Plus.
Wait, what?
plus b
Oh,
e
it's the product thing.
to the minus 40.
Yeah.
And x's speed is 4 when x is in the positive direction. It's just saying that they match each other. So we get 4 equals, oh, I actually knew that a was 1.5. I probably could have dealt with that.
Minus 4a
Minus 4a
plus b.
plus b. So 4 plus 4a, 4a is, well, 1.5, sorry, 4 times 1.5.
B still, oh no, this will be another second one.
So you just get 4 times 1.5 is 6, plus 4 is 10, so b is equal to 10. So the particular solution is x equals 1.5 plus 10t e to the minus 4t. And they want us to find the value of x when t equals 1. So x equals 1.5 plus 10 e to the minus 4, which is typed into a calculator. So that's 11.5 times by e to the minus 4, which is 0.211 meters to 3 significant figures. I'm going to graph it as well. Why not? Can I do a new graph? I don't know how to do this. So it was y, I'm going to have to change it to y equals 1.5 plus 10x e to the minus 4x. Okay, so it appears to move a little bit further in the direction that it was moving in initially, and then critically it moves back to the equilibrium position. So it's a critical damping for that particular example, and it's critical because of the repeated roots that resembles this one. So it's critical damping. There is no oscillations. Right, what am I doing? Next page. Next question.
2 more examples.
2 more examples. Bloody hell. Let's go quick. Particle hangs freely in equilibrium, attached to one end of a light elastic string. The other end of the string is attached to a fixed point A. The particle is now pulled down and held at rest in a container of liquid, which exerts a resistance to motion on P. P is then released from rest. While the string remains taut and the particle in the liquid, the motion can be modelled using the equation blah blah blah. Find the general solution to the differential equation and state the type of damping that the particle is subject to. But they've told us what it is, and they haven't even asked us to show that that's what it is. So who cares, right? But if you were to think about what this looked like, you've got something that is on a piece of string inside some liquid, and it's being pulled down. So there is going to be some kind of tension that is pulling it up, and there's also going to be some kind of resistant force, which is to do with the liquid, okay? When you put all of those things together, they've told you that it comes up with this differential equation that we've got. All they want us to do is just solve the differential equation, so we're just going to solve it. So we've got the second derivative. I'm going to save a bit of time when I write this out, plus 6k, the first derivative, plus 5k squared x equals 0. What do I do first?
Auxiliary equation.
Auxiliary equation. What's the auxiliary equation, Luke?
M squared plus 6k L plus 5k squared.
Okay.
How do we do that?
Yep. So find the general solution. Well, actually, we,
M is
M
minus
plus
1.
5k, M plus 1.
Yeah, M is minus 1, M is minus 5.
okay. So you're going to do m minus. What did you say?
It's M plus 5, M plus,
M
plus
plus
1.
5k.
M plus 5k and m plus
Okay,
k.
sorry, my bad.
So either m is equal to minus k or m is equal to minus 5k, which means that x is equal to a plus, not bt, a e to the minus kt plus b e to the minus 5kt. Okay? And that's the general solution to the differential equation. What's the type of damping?
This one, 2 roots.
Heavy,
So it's,
heavy.
is it heavy?
Yeah.
Yeah.
Heaving. Going to combine all my words into one. Heavy damping.
You damn.
Struggling. So heavy, struggling.
Heavy damping, okay? So it's a really easy question. So let's power through. Next example.
Are we done? How many marks is that?
This, 4. Yeah.
Wow.
Yeah, even though there's a lot of
4 more.
words.
Yeah, I mean, like, all of this is just like...
Nothing.
Irrelevant.
But you can see what's happening in the situation, right? That the liquid is an additional force that's going to be slowing it down. It's not going to continue bouncing because the liquid is resisting its motion.
Would you take, if they ever tell you to do it, would you take upward thing into account?
No. No. Because they haven't mentioned anything about upthrust, so I would think we'd ignore it, okay?
Should I show everyone do
Don't do this. Don't do it to yourself. Sounds interesting.
Okay, next one.
Don't do it to yourself. Trust me. You don't want to join the
Are
group.
they talking about suicide?
Okay.
One end of a light elastic spring is attached to a fixed point A. A particle P is attached to the other end and hangs in equilibrium vertically below A. The particle is pulled vertically down from its equilibrium position and released from rest. A resistance proportional to the speed of P acts on P. The equation of motion of P is given as, here it is. They've just told you what it is. But basically, you've got a spring with a particle on it. When it moves, if it's moving in that direction, there is a resistance to motion of, we don't even know because they haven't told us. So they've just told you what this equation is. Our equation is x double dot plus 2k x dot plus 2k squared x is equal to 0. And all they want you to do is find the general solution and talk about the oscillation of it, okay? So there's going to be some kind of oscillation here. What is the auxiliary equation?
M squared plus 2km plus 2k squared.
Okay,
M plus k and M plus 2k. Is it? Damn it.
no. So I know, There's got to be something complex about it. How do I know there's something complex?
Because 2 and 2, no factor of 2.
Yeah, but there's something in part B that tells me it's got
It's
oscillations.
like, right?
Yeah, and it does say here, find the period of the oscillation. So I know it's going to have sine or cos in it somewhere. So if you want to solve this, you have to use what?
Maybe it's minus k.
Pardon? You could do completing the square.
Is it minus k plus minus
Well, you can't because it's k.
Well, I would probably just use the quadratic formula, or I'd complete the square. I'm gonna.
How do you do it?
How do you do it on the calculator?
You just
put it without the k's and put the k's in after.
Where do you put the k?
Fair enough.
You can do that?
Where do you put the k though?
That's what I
know
did
what?
with
So you got.
Oh no, he's right.
Anyway, I'm going to do it as m plus k squared minus k squared plus 2k squared equals 0. I'm going to complete the square like Luke would do. So you get m plus k squared equals k minus k squared. So you get m plus k is equal to plus or minus ki. So m is equal to minus k plus or minus ki. Is that what you got?
Different by k. Whoa.
Yeah? Which means that the general solution is x equals what?
E to the minus k t.
It's pretty smooth, yeah.
The a of t cos k t plus q sine k t.
Nice.
Okay, so that's the general solution. That's part A that's done. Part B says write down the period of oscillation. Do you remember how you find the period of oscillation?
Pi
2
over
pi
omega.
Good. So period is 2 pi over omega. What's omega in this case?
2k squared. 2
K.
K.
Just
But
k.
do you want to just say any more things? You've
Just
said about
K.
everything that's on the board. What is it?
Just k.
It's just k. It's this thing.
Yeah.
Because remember that because the graph normally has a period of 2 pi, but because we've got the k in front of it, we've compressed it by a factor of k. So the period of oscillation is the usual period 2 pi divided by it. So
Isn't it
Omega
omega
squared
squared
at
x?
the, yeah, so I'm confused.
That's what I'm thinking.
because that
2k squared at the top.
Is
Is
it?
equation.
No, it's not.
no, because it's damped. So this is the omega bit here. Omega is k.
No, when we make the equation, we said this
Because
is
that was
omega
for
squared x.
no,
But that's for simple. That makes sense.
but that is
That's for simple.
Oh, lol.
because everything's been doubled. It just does. It isn't. It just isn't. This is the omega here.
Omega lol.
So it's 2 pi over k.
I'm trying to understand. He's an idiot. Shine omega.
Why? Okay. Why? So we've said it's omega squared x. But then it's got a different factor in front of the k. So the fact that this k appears in both of them in R1 means that you can't just look at what that pattern is. If it was just a k, then the omega there would be root 2k.
Sure. Let's just go with
It's
it.
because they don't match. It's because it's not exactly the same as the previous form. So the period is 2 pi over k seconds. So we'll do a couple of questions from exercise 8C, and then in about 15 minutes we'll do forced harmonic motion as well.
If you don't get the